Hi, welcome to this session on the third session in deep learning for computer vision. And yeah, it's starting now. It's starting just now. It's from 6. Yeah, so welcome to this session, and this is the third week. And today we'll go through some feature matching techniques as well as the code for it. So, hope you'll find it interesting and helpful. So, in this week, sir has already talked about, so let me share my screen quickly. Yeah, I hope it's coming up. Yeah. Okay, so just give me a second. Okay, got it. Yeah, just a second, just give me a second. Okay, yeah. So, we'll begin our session today, and today will be about some feature matching techniques by which we can. So, last day we had seen SIFT. So, SIFT was like a feature descriptor method. So, given an image, it gives you some interesting points in that image and the feature descriptions for those points. And now what do we do with those descriptions? That's the question, right? So why do we at all need these descriptions given an image? What is the use of finding these interesting points and then finding the image descriptions for it? So today's session will be more focused on that. So we'll talk about some feature matching techniques and the most popular algorithm from them that we'll talk about, and the code for that also we'll visit and see. And also we'll talk about some other methods like bag of words, which are like another way of describing the features of an image. So while for example SIFT, if you remember, if you have attended last week's sessions and if you have gone through the lecture notes, so SIFT kind of gives you feature descriptions descriptors for many interest points in the image. And so we'll talk today about some algorithm which kind of gives you a global feature vector for a given image. So instead of giving you multiple feature vectors for multiple interest points in a single image, it will give you one feature vector for one image, and we'll see how we can use that in a good way. So let's begin. Okay, so like I said, feature matching. So coming back to the question, now we were detecting interest points last week, and we were we were talking about feature descriptors like SIFT and all. So here we'll talk about why these interest points are important at all, right? So here you can see that this is a source image and this is a destination image, and probably they are looking at very similar areas, right? So this is a scenery of mountains, and you can see that both the images are probably depicting the same range of mountains, just that they have been taken from two different angles. Now what you want to do is you want to find a correspondence between this image and this image, because they are depicting the same thing. So whatever you see in this region is similar to whatever you are seeing in this region. So it's like a rotated version. So it's as if your image has been shifted, not rotated, it has been shifted from here to here, and the image has been taken from there. So that is what we so given such an image, you want the computer to know that okay, you in these two images you are looking at the same thing. Okay, so this point that you see, these three red points on the mountains that you see here, the parts that they are looking at, they correspond to this part in the destination image. That's what we want to tell the computer. Okay, so that is why. So exactly, if you look at if you tell me that Yeah, we can do an L2 matching. I mean, we can just match the pixel values here and here. That won't work because maybe you took an image here in one lighting condition. Maybe when you took the image here, the lighting condition changed a little bit. So the pixel values may not be the same in these two locations. So that is why we need help from the feature descriptors that we saw last week in order to detect the interest points and the descriptions of each of those interest points. Right. Another application can be, the most common one is your panorama images that you click on your mobile phones, mobile cameras. So basically you are asked to take a 360-degree image of your surrounding, the entire surrounding that you have, and you are asked to take a picture of that, and your mobile device is able to stitch them into one single long image, right? So wide image. So this image stitching is another application of this feature matching. So in order to do that, so the computer machine or whatever machine you are operating, it has to know that the first image that you take and the second image that you take, they are like very the second image is like a very small variation of your first image. So that is what you mean by, so by knowing that, the computer will then know how to stitch this image with how to stitch this image with this image. So that is what is known as feature matching. So there are some methods of feature matching. So these two, dense registration through optical flow and wide baseline spatial matching. So these are very popular methods. However, there is a problem in these methods. So the problem is that if you look at this, if we go back to this example, so these methods will only work if the source image and the destination image are like this. But what do I mean by like this? That these points are getting translated here in the destination image, but you can see that the displacement is not that much. So there is a very small displacement between the original points and the destination points. So these two algorithms only work when you have when your displacement in the two images is very small, that is the two images are actually very similar in nature. But I might give you an image which is not very similar. I might give you a rotated version of this source image. I might give you a flipped version of this source image or something like that. So where the displacement is just not as small as what you see here. So the question then comes that if the displacement is not that if it's pretty huge, if it's a big displacement, then what do I do? If the images are same, but if they are like rotated versions of each other, then what do I do? Then the distances won't be that small like what you saw. So for that we will talk about this ransack algorithm. So this so this is the focus of our talk today, the ransack algorithm entirely. So here we are looking at an algorithm which basically ensures that if you have some displacement in the image which is very big, which is like an outlier sort of compared to these ones, then how to manage the entire situation. Okay. So in this algorithm, so like I told you, the previous methods, why they fail because they fail when the source image and destination image, they are not really like small variations of each other, then the previous methods fail. So this algorithm ransack, so I'll go to an example and show you why this is helpful, but it's much easier to understand it from the point of linear regression. So so what we do here, what happens in the least squares method or the curve fitting method. So you have been given suppose a list of points like this, right, which you have plotted, right, in some space, and you are trying to fit a line onto them. Okay. So normally if you don't consider this blue point that I am marking here, let me use the laser pointer. So this this blue point that I am marking here with the red laser pointer, let's ignore that for now. So if we only had these few points, then we could have easily drawn a line which would have gone like this, somewhere covering all the points, right. So that is the linear regression least squares method which would have fitted this line. However, that method is not robust to outliers. Why? Because suppose this point which is suddenly out of the way of these all these points which were kind of lying in a straight line. So this point is what we call an outlier. So suppose this is, so you can already see that this point is lying somewhere here. So the question then comes that how do we then, if the point is coming here, then what happens to the linear regression solution? And we see that the straight line, while normally it would have been somewhere around here, the one that I am marking, it is moving this way, right, in order to incorporate this outlier point as well. So it's not, it's in order to incorporate this outlier point into this particular fitted curve, it's making a error on all of these points, right, it's ignoring all of these points in order to cater to this point. So that is actually bad. What we want is, so I mean many research has gone into finding a method which for regressing where your fitted curve, fitted line actually is robust to such outliers, because I do not need to, because this being an exception, all of these points are like this. So this being an exception, I do not need to focus too much on this point. It's okay to focus on these points only. So I need a method that is robust to such disturbing points, disturbing agents. So that is, ransack is such a method which actually does this. Okay, so here in this slide we have kept an algorithm, but I think it's better to just give you an example of how we do it in a simple way. So suppose like ransack is a iterative algorithm, right? So what we do is very simple thing. Suppose I choose two random points. So suppose this last one here and this one here. Okay, so if you have 2 points, right, so that means what, that there is only one straight line that can go through these 2 points. Okay, so now what I'll do is I'll draw a straight line between this point and this point, the ones that I chose. So these are chosen randomly. Okay, so I'll draw a straight line, okay, like this, the one that I am marking. So the exact straight line is not available with me, but just imagine that I am trying to join this and this, and I have drawn a straight line through these. Now what I'll do is I'll see for the straight line that I have drawn, I'll just see whether, you know, in a small neighborhood around this around that straight line, how many of the other points are coming in. Okay, so I've again drawn this line. Okay, drawn this line through the entire plot, the line that is joining these 2 points, and I am basically trying to see like how many points are kind of like falling around this line, very close to this line. Okay, so suppose I see that when after I draw this line, only these 2 points are kind of like coming in the similar neighborhood. Okay, so now we know that the number of points that are lying in the neighborhood is 2. Then what I do in the next iteration, I'll again select 2 more points. So suppose I select this and this, okay, the ones that I marked, this and this, and I again draw a straight line through them. Okay, and now I see that 5 of the points are coming in the small neighborhood around the drawn line. Okay, then in the next, so I see that 5 is better than the 2, right? Previously these 2 were coming in the neighborhood. Now I am seeing that kind of like 5 points are coming in the neighborhood. So 5 is greater than 3. So I discard the first 2 points that I had selected, and I choose these, I save the results for these 2 points. Okay, the line that I drew for these 2 points, that I save. Now I again move on to some other line, like for example, I move on to some other points, like so for example this time I select this and this, and I again draw a line through them and see that around the small neighborhood what are the number of points that are lying. So this time I see 0, and I know that this particular line that is joining these 2 is not good enough. So I discard it once again, and I keep repeating this process for a fixed number of steps. And so remember that I had already saved the best one, right? So till now my best one was this, the line joining these 2. So at the end of the algorithm, at the end of a few iterations, the best result that we have, right, so the best result that we have, that we are going to store. me a second. Nimesh, can you please mute yourself? Thanks. Cool. Okay. So this is how this ransack algorithm works. So if we go into the math part of it, so this is the data. So these are the data points that we saw. These blue points are what our x is, and n is the minimum number of samples that we use to fit a model. So this will depend on the model that you want to fit, but here we have taken n to be 2 because that is simple to look at, that can be changed, right. And now S is a scoring function. Okay. So now given your 2 points, you are trying to like see what is the MSE score or something like that. You are trying to score your model based on the parameters and the sample x. Now what you see is you repeat, like I said, this is an iterative method. So you draw n samples from H, which is a subset of x at random remember. So here n, we had considered n to be 2, that is why from every time we are selecting 2 points at random from the list of points that we have, and then we fit model to H and compute the parameters theta. Now we compute this score, right. So this score is going to give us like how good our method is. So for example, we said that we are going to look at the number of points around the neighborhood of the drawn line. So we will see if at every iteration, if our selected set of n points, n equal to 2 in our example, if we get a score S star which is greater than the original S, we are going to save the parameters and we are going to save S star, and then we are going to move on to the next set of points, and we will repeat this for a fixed number of iterations, and at the end of the algorithm, at the end of running this algorithm, we are left with some score S star and some theta equal to theta star, which is supposedly a very good fit to the entire data set, which is robust to this outlier point, right. So you will get to see an application of this algorithm here itself. So I hope this is, let me okay, yeah. So I hope this is visible. So like I said that you can see that so the point of starting this entire conversation was that your source image and destination images may not be very close to each other, right. So here it is very close, it is just like a translated version of the source image. But if you look at this destination image, so you will see that not only is it rotated, that much you can see. So this one is a rotated version of this one. This is the source, this is the destination, and another thing is that you can see that the resolution itself has changed. It is not the same resolution as this. So this is wider and shorter or something like that. So now you can see that, so these points correspond to, so you can see all the correspondences are matched over here, right. So they are all of the similar they are very similar in nature. However, you can see that this point corresponds to this point, which is an outlier in nature, right. So that is where this outlier thing comes into existence. So this thing you can see that while this is below, this thing translates to here in the second image. So in the rotation cases, the things are not as simple as the first image that we showed, and hence an algorithm like ransack usually helps. So however, one problem with these ransack sort of algorithms is something like this, that okay, so whatever we were doing till now, even in this particular image, suppose we are looking at this signboard, and this signboard is exactly a rotated version of this signboard. Similarly, going back to the first example, this particular mountain peak that you see, or mountainous range that you see, this is exactly the same mountain range, just a little bit maybe translated towards the right, okay. But suppose here I give you a image of the Everest, here I give you an image of say Kanyakumari, which is, these two are very different, right. These two are definitely not the same. They may look very similar, they have very similar characteristics, like they are peaky, they have snow, etc. But these two are very different in nature. So Now these feature matching algorithms that we have enlisted here, all of these are capable of matching images, matching features when the two images are very similar in nature. They are depicting the same thing but from a different viewpoint. So in all these cases these algorithms are fine. However, if you suppose like if you can look at this particular image where this is a small helicopter of a certain model suppose, and this is a large helicopter of a different model. Also this here the background is that of jungles, and maybe there is a river here which is not very visible, but this image you can see that it's in a it's kind of looks like an airport with buildings and all. So here not only are the helicopters changing, the backgrounds are changing as well, right. So this is one of the failure cases of these algorithms, where you can only take into consideration images that are very similar to one another, whose objects are similar, whose backgrounds are similar. So here applications are like the ones that I told you, image stitching or something like that. But in order to, so the model, if you give a ransack algorithm these two images, while a child would know that okay this helicopter and this helicopter are the same, the ransack algorithm wouldn't know that, because they are very dissimilar in structure, right. So there is a lot of differences in how these two look like. Okay, so now we have to come up with, so that is the next step. Okay, so like how do we deal with the same object but different instances. So other examples being like I give you a Maruti car and a Honda car. So can the algorithm identify that both are very similar in the sense that both are cars, right. Similarly different dog breeds, cat breeds and so on, even two different humans, two different girls, two different boys, how do I know that they represent the same family of objects, that is humans. So to do that people have come up with two algorithms. One is bag of words and one is VLAD. VLAD is just an extension of bag of words. So all of these have been covered in the lecture classes. So it will be best if you go back and have a look at them, and you'll understand them much better. But yeah, I mean here our job is just to give you some sort of revision of what is going on in the classes, in the lecture sessions. So bag of words. So let us go into that. So like the name suggests, so this is something, some algorithm, some tool that is very useful in the text world, in the natural language processing world, right. So in natural language processing or in text, you have multiple if you have a sentence, you have multiple words, right. So bag of words, basically like the name suggests, you are basically taking all the words and putting them in a bag, right. And now okay, so what you are trying to do is you have a bag of many words, okay, and that is called a vocabulary. So you have a large piece of text, okay, maybe millions of sentences are there in that piece of text. You take in all the words in that text and you keep them in a bag. All the words that you have seen in those millions of sentences, you have kept them in a single bag, right. And now when a new sentence, so and now you will see, like suppose I give you two sentences like for example what I am going to school and suppose like I am going to college. These are the two sentences, right. So here you can see that I am going to is the common element in these two sentences. So now I'll first I'll put all these words in my bag. So I am going to and school, I am going to and school, all these words will be put in the bag, and also from the next sentence you will again put all these words into the bag. And then if you have a sentence like for example suppose what my school's name is Kendriya Vidyalaya, right. So now you want to, so this is a third sentence and you want to find out, like given the two sentences that I told you, what is the most similar sentence to the one that I just said. So because both are talking about schools, I am going to school is more similar to my school's name is Kendriya Vidyalaya. So yeah, so sort of a thing where you know, your content of a sentence is compared with other sentences to match the two sentences, to match the meanings of the two sentences, is what is known as bag of words. So let's so this example will make it much clearer actually. So what you do is, so suppose you have a training set, right? So training set, for the unversed, training set is something which you are using to train your model, to make your model learn what is there in the world, basically in the universe. So suppose like these are the 3 images that you have in the training set, okay. So now what do you do with, like in text, what I do, I take each of, suppose in text, instead of images we will have sentences, right. So we take each of the sentences, we break them into words and we put the words into a bag. Similarly here I have 3 images, I break all the images. So for example, from the face I will take out the eye part, nose part, mouth part, hair part and so on, and I will put it in the bag. I take the cycle, I will break it into tire and pedal and suppose seat and so on, and again I will put it in the bag. In the violin I will again make small changes, I will take this one, maybe this part and this part, etc., and I will put all of this in the bag. So our bag, which is called the vocabulary, looks something like this. So you can see that so we are kind of like creating features, but the features will be created in a while. So they are not yet created, I am showing like how we are going to create the features. But yeah, the objective of bag of words model is to create features for each image. So you will see how to do that. So now, right, so you put all the different parts of the image into the bags, and this bag is called your vocabulary. So it has like seen different, you know, images, and it has seen different parts of it, and it has put those parts into the bag. So now comes that, given this image, how will I form the histogram for it? So all these, how many are there? 1 2 3 4 5 6, again here maybe another 5, here maybe another 7. So that becomes your vocabulary size. Suppose let's say the vocabulary size is 20, right. So in order to vectorize this particular image, I will have a 20 dimensional vector. So my dimension of the vector will be same as how many you know, small patches I have collected in this vocabulary. So I have a 20 dimensional vocabulary. Now what I will do is, I will create a histogram of the elements in the vocabulary based on this image, right. So for example, I have 2 eyes here. So here the space that we had reserved for the eyes, that will have a score of 2. Similarly, I have another, maybe some other patches which are relevant to faces. So we'll find them and we'll add them to our histogram, whereas all the areas which were reserved for the cycle tire, for the seat, etc., they remain empty, right. So this is how we create the histogram. So we have a 20 dimensional histogram, and given an image and the different parts of it, the patches that we find in the image, we are going to put them in the histogram, and that will give us a 20 dimensional vector. So suppose here, like for example, they have shown only 4, but suppose it's like this, that this count is 1. So suppose we can do something like this also, that we can convert this histogram into a probability distribution just by dividing all of these by the sum of these all these counts. And so suppose this is 0.1, this is 0.8, this is again something, and so on. And the later parts, so these 4 parts are okay, the other 16 are all empty. So I said that it's a 20 dimensional vector. So that becomes our vector. So it became it's a 20 dimensional vector whose first element is 0.1, whose second element is 0.8, third element is again 0.05 suppose, and so on. Similarly, when you go to the cycle image, a similar thing you can use. So you find out what are the you take the different patches of the cycle, find out what are the similar patches that are there in the vocabulary, and you basically start increasing the count in the histogram. So here again you will not find any similarity with the human parts or the violin parts, you will only find similarity with the cycle parts. So, there you will get in those dimensions you will get non-zero counts, otherwise you will get 0 counts. And now you can either use them directly, or you can convert it into a probability distribution, and you can use the decimal values, and similarly for the violins. So, this is how for every image you can get a vector. Now, there are other questions that we have to look at, like how do we suppose every human's nose is different, right? So, how do we even match that this nose is similar to this nose in the vocabulary, and what happens when a new image comes? So, these are our training images. So, we have already taken parts of it and put it into the vocabulary, right? So, what do we do when a new image comes up? So, here I mean yeah, it's a bit involved, but let's okay, let's yeah. So, I think this will be a little bit clearer. So, okay, let's do this once. So, let's go through this slide. So, this is a little bit writing is there, but I think we can manage. So, what we want is for each image to be represented by a vector z, okay, which belongs to Rk, where k is the size of our code book. So, code book is nothing but the vocabulary that we created out of the training images, right? And now, what each component zi, so each component of that vector z will contain wi times ni, where wi is some weight. So, you can either not have any weight, or you can keep a fixed weight where the weights all sum to 1, okay, and per visual word. So, all these elements that we are storing, the individual parts of the face, the cycle tire, etc., seat, etc., these we call visual words. So, basically we are trying to translate our image to a text, to a piece of sentence. It's as if the image is a sentence and the individual parts of it are like words. We are calling them visual words, right? And here we are here. So, ni is the number of occurrences of this word in the image. So, how many times the eye has come in the image, how many times the nose has come in the image. So, that is given by this ni. This is the count in the histogram. Yeah, this is the count in the histogram. Now, suppose for now let us assume that we have been able to create. So, given a set of n images represented by vector z, where z belongs to R k cross n. So, suppose we have our training set of n images and z is our training matrix, okay. So, we have basically the just the way I said. So, these histograms we have taken the training images, we have created the vocabulary. Again, we will talk about how to create the vocabulary in a bit, and we have created the histogram, okay. And so, for each training image we have a vector of size k, and we have n images, right. So, that is given by this matrix z, okay. So, now we have these training images, and what we want is, suppose I give you a new image. Suppose for example, given these 3 training images, I give you the portrait of Mona Lisa, and I tell you that ask you that out of these 3 images, what is the most similar image to the Mona Lisa image. So, you can see that this image and Mona Lisa image, because they are different, the previous algorithms like ransack won't work here. So, you need to tell the model that you need the model to understand that they are both humans, they are both maybe ladies, and so it has to retrieve some lady image from here. So, now what it will do is, so suppose I take the Mona Lisa image, and so that I am calling as q, okay, very simple thing. So, I take this Mona Lisa's image, I represent it as a similar vector, okay. I know how to vectorize the Mona Lisa image from here by creating the histogram. So, I have a vector q for the Mona Lisa image, and now all I need to do is I need to find that in my matrix z, which consists of all the training images, what is the closest one, okay. That you can do in multiple ways, right. You can find cosine similarity between the 2 vectors, you can do L2 normalization, you can find Euclidean distance and so on. So, lots of things you can do. There are yeah, okay, did I okay. Yeah, there are lots of things that you can do in order to compute the distance between your query Q and the training images Z, right. So, this is not important that how you compute this score smallest, but you can use anything for this. So, you have to keep trying, you have to what algorithm, what method you use to compute this is dependent on your application as well, right. So, now with this what you have done is, if you have n training images, suppose n equal to 3 here, you have 3 scores for the query Q. You have 3 scores for the query Q, and all you are doing is you are setting those scores, sorting those scores in the descending order, and that you are giving as output. So, if you, for example, if you have these 3 training images and Mona Lisa's image is a test image, then this one will have the highest score, and these two obviously they will not have any meaningful scores. So, their scores will be much lower in that respect. Okay. So, correct. So, here like for example, you can very easily see that so this is like one example. So, here you have what do we call it. So, here you have two training images, and you are trying to basically match up this query image with these 2 training images. So, what you are doing is you are finding the visual words in the query image. So, already the vectors for the training images are available with you. So, now you are trying to find the visual words in the training images, you are computing the vector out of it based on your vocabulary, and now you are taking the vector for the query and you are trying to match with the these 2 training images, and you are trying to score them either with cosine similarity or some other scoring function to see which is the closest image. And here it shows that this one, it seems like this one is the closer image, even though probably this also is very close, but this one is still closer. So, you can see that because the images again, like because the images, even though they depict the same thing here, your algorithms like ransack etc. won't be working here, because suppose here for example there is a human, here there is no human, here there is the ground, the green part, here there is, you can't see the ground at all. So, that is why feature to feature exact matching is not a good idea. I mean, it works in many cases, many applications like panorama creation, but it does not work when you are trying to match 2 different things or things in very different backgrounds and so on. So, that is how bag of words retrieval helps. So, now one idea can be that how do you classify, okay. So, classification is like a basic task in machine learning, right. You will get a more formal definition perhaps next week. So, what do you do in classification, in supervised classification? Suppose you are given a data set of cats and dogs, very simple, right, and now you are training a model, machine learning or deep learning model, whose task is to first learn from the given images what are cats and what are dogs, okay, and then given a new test image of some animal, it has to say whether it is a cat or a dog. So, that is in a nutshell what a classification algorithm is. So, now this particular slide basically summarizes how you kind of like generate the visual words in the image, and how you find the how you basically create the vocabulary and then the histogram. So, what you do is, using suppose your SIFT or some other feature descriptor, you extract the interesting key points and their feature descriptions, right, and you stack them in this particular say vector or matrix. So, now the difficult thing that you can see again, if I go back to this image is, so I mentioned a while back that suppose this person's nose is like this, but now maybe I give you another training image where there is a man whose nose looks something different, somewhat different, right. Then I give you a maybe dark colored person whose nose looks a little bit more different. So, it is not very easy to collect all of these. So, will you store all of these 3 different noses separately, or would you rather prefer to have something which is similar, right. So, what you, oops, where am I? Yeah, here. Okay. Yeah. So what you do is, so you take the images 1 to n, you extract the key points, you extract their feature descriptors, and then you combine all these descriptors. So if you have like 100 descriptors, 100 feature descriptors from here and maybe 100 from here, so n suppose is equal to 5. Okay, so then that means that total you have 500 descriptors, and you do not know what descriptor is basically describing what. So descriptors are not readable, human readable, right? So they are just numbers, they are like vectors. So what you do is, like it's written here, so you fix a, you do k-means cluster, you do some clustering algorithm. So you run some clustering algorithm on these collected features, and you choose a certain k, suppose k equal to 20, like I said. So k here stands for your vocabulary size, like I said, right? So you set k equal to 20, and you take all these feature descriptors that were there, and you run this k-means algorithm on top of this. So k-means is nothing but a clustering algorithm, and a clustering algorithm's job is what? It will group the similar things together, right? So that means what? That it will group the all the noses together, it will group all the eyes together, and so on, based on your the k that you have defined from beforehand. So if you have defined a k equal to 20 from beforehand, it will create 20 different groups of similar things. If you define it to be 100, it will create 100 different groups of similar things. So this is how. So if you create a k equal to 20, then it will create 20 groups out of this, and those 20 groups become your 20 different vocabularies. Yeah. And now what you do is, given this training image once more, based on okay, yeah, given your training images, given this training image, you find out like what these individual key points, so individual feature descriptors, what clusters they fall in. Okay, so now like what clusters they fall in, that you find out, and how many feature descriptors are there. Suppose you basically count the frequency of each of them. So suppose you had 20 different, you want 20 different like your code book or your vocabulary dimension is 20. So now you take the first one, and you see like how many times this has appeared in the first image, and that becomes your histogram count. This is how you create the histogram. So clustering first, because you have a lot of features, lot of key points in the images. So you do a clustering first with a fixed predetermined k, and now once the clusters are formed, given all these feature descriptions one by one, your clustering algorithm will tell you which clusters they belong to, and you will do a +1 in that particular dimension in the histogram, right? So this finally helps you generate the vector. Yeah, so this finally helps you generate the vector that is there, and so this basically leads you to create the feature vector of the given image. So like I told you in the very beginning, the first sentence that I probably used was that the SIFT features that we saw last day, they like give you so many key interest points like it's shown here, and you get one individual vector out of all of these, right? So you get all these vectors out of a single image. And now the bag of words method gave you one vector for the entire image. Okay, and now these vectors that you get from all the training images, you can send them to some models. If I am hoping that some of you at least know what are the traditional machine learning algorithms, you have heard of them at least. So SVM is one such algorithm which performs the classification task. So you give these vectors that you get as input to the SVM model, and the SVM model will learn what are the dog images, what are the cat images, right? So this is how you perform classification. Yeah, so this is how you perform the classification task in the bag of words setting. So yeah, so is there any question on the bag of words part? You can just ask me. Okay, then I'll move on to the coding part. Okay, so here for this week we are focusing on ransack. So we'll walk through the code of the ransack algorithm. So both you and me will learn like how to like the nitty gritties of the algorithm. So like I keep saying, in order to learn what goes on in an algorithm, it's very good to have a look at its code, because a lot of it is not mentioned in the algorithm and you can find those details inside the code, and it clears a lot of confusion. So now what here we are trying to do is we are trying to perform regression with ransack for robust curve fitting. So we have already discussed that ransack gives you robust curves. Let me admit, yeah. So we have already discussed, that ransack gives you robust curves. So what we are trying to do is we are trying to fit a particular polynomial to certain some given data points. Okay. So we have so we know that, I hope we all know that we know this formulation of polynomials. So for a given polynomial we can express it in the form of matrix X, some response vector or some y and a parameter vector. So y is given by this beta 0 plus beta 1 xi plus, so y, this is the ith data point, beta 2 xi square and so on up till beta m xi to the power m plus some plus some error which is epsilon I. And now so as we all have seen in our preliminary linear algebra classes, so given a system of equations we can set them in this way. So we have like so how many coefficients do we have here? We have m plus 1 coefficients and we have n such equations, okay, and that we can write in this way, right. So I will move the highlights here. So in the vector or matrix notation it looks something like this. So you have the y's here. Yeah, go on. Srijana, I think you have raised your hand. Can you please unmute yourself? You are not audible. Oh, is it not visible? Okay, okay, I'm very sorry. Thanks for mentioning. Yeah. Yeah. Thanks a lot for pointing this out. So we are performing here regression with ransack for showing that ransack has robust curve fitting capabilities. So we are trying to fit a polynomial to this data set where you are given a you are given xi and yi points, okay. So here like there are, so this is how a polynomial looks like, right. So you have you express a polynomial in terms of a matrix X and some response vector, suppose y, and a parameter beta, okay. So just give me 1 second, I will just plug in my laptop, it is running out of charge. Yeah, sorry about that. So yeah, you are expressing like we have all seen in our like we have all seen in our linear algebra classes. So we can express equations in this form. So there are, so this xi goes to the order of m. So we have coefficients starting from beta 0, beta 1, beta 2 and so on up till beta m, and so xi, so we have here xi to the power 0, xi to the power 1 and so on until xi to the power m, and we need to solve for these betas, and there is an error also associated which is epsilon I for this ith point. So this, like I said, we can we generally, so in order to solve for these we have a system of equations and we have n data points in total, n for Nagpur here. So we can express them in this way. So y1 equal to so basically beta 0 plus beta 1 x1 plus beta 2 x2 x1 square and so on. So this is given by this particular line, the first line, and so on. So I hope you understand this, and so this is basically, and you are adding the epsilons also in the side. So in the matrix notation, so if you have n equations and m such coefficients or m plus 1 coefficients, you can express them in this way, and in a shorter notation it looks like this. So y, which is the vector y, equal to x into, so this is the x, entire x, into beta, beta is your unknowns, so it is a vector of unknowns, plus some epsilon. Okay. And now when you suppose if you go back and solve it in the least squares using the least squares method or whatever, this I will not go into, but this is something very fundamental that we find out there. So for this system we can calculate beta, so beta is our unknowns, by using this particular formula. So beta equal to x transpose x whole inverse x transpose into y, right. So this is something again that is very fundamental result, and if somebody is not aware of it or has forgotten it, so you should go back and look at it once more. Okay. So again, what is the function of ransack? As I said, we want to avoid outliers in our curve fitting, and hence we will calculate. Like we said that we will take some points at a time, we will try to draw curves through them, we will try to look at their neighborhoods and see how many points are there inside those neighborhoods, right. And based on that, whenever we reach a new best set of points, we will save the corresponding parameters, right. So we will calculate, like it says, we will calculate multiple beta i's using a set of data points. So it is an iterative way, iterative algorithm. So in every iteration we will take a fixed set of points, we will try to fit a curve on those fixed set of points, we will try to see what are the points in the neighborhood. If the number of points in the neighborhood is higher than the previous iteration, then we save, otherwise we move on, right. After calculating several beta I, we will find the best value of beta using least squares. Okay. So we will start first with the import statement. So this we have already gone through a couple of times. So we import numpy. Pandas is another very important and handy library for which is helpful for storing and visualizing data. So matplotlib you already know, sklearn we have already seen some maybe 1 or 2 weeks back. So all these you can see that sklearn, these sort of libraries, they basically have implementations for all mathematical formula that you can think of. So so just go through this, Google it and try to learn as much as you can, and it basically has many of the mathematical calculations that you would want to do in if you want to write an ML code. Okay, so let's go into the regression part. Okay. So first, so everything is commented here, so you can just have a look at the initial comments to know what we mean by the individual variables. So the first thing is the order of the polynomial. So order of the polynomial is given by this m, correct, and bias is basically so you get to know about bias basically, and so you so here they are saying that it's a boolean. Okay. So whether we need a bias term or not, that is what it's saying, but we will go into it later. So so first you initialize. So in the initializer you are already defining what the order is and what the bias is. So you save them here in the class variables, right, and then you have a beta which is like np.zeros order plus bias. So what does this tell you? If your order is m, right, so you have this beta 1 to beta m, then what is the bias? Bias term is basically this beta 0. So you are saying generally very often beta 0 is set as 0, okay, but here you are trying to say that you have a bias term which you want to learn. Okay, this is not known to you from beforehand, but you want to learn this beta 0 term also, which is actually not associated with any of the x's, because it's basically xi to the power 0. That is what the bias term stands for. Okay. Now these two we are initializing, and we will see later what the use of this is. Okay. So number of iterations we are setting to be 0 for now, and some probability we are setting to be 0.99. Okay. Now this function, as the name suggests, so this is something that is useful for later. Okay. So suppose you are already storing the beta, right? So beta is your unknown, remember. So suppose I give you an x vector, and so this predict function will do what? It will, based on your x vector and based on your this beta equation, so the beta that you have, self dot beta, it will basically generate the beta 0 plus x1 or xi beta 1 plus xi square beta 2 and so on. So this is what it will generate. It will generate the y hat, the predicted y hat, based on the beta that you have obtained for now, right? So this is what the predict function looks like. So it predicts an equation using polyfit. So you can just look at these functions on your own time, poly 1D and all, what they do, what functions they exactly play, but this is in a nutshell what the predict function does. Now we come to the solve function. Okay. So solve is basically this is the main function which you are using to solve regression using RANSAC. So you have the x as the input, y as the output, and what had we defined as n? N was the number of data points that we are using to do our temporary curve fitting per iteration. Okay. So in the easy example that we had shown in the slides, we had used n equal to 2, and iterations is number of iterations to find the best beta. So you can see that here we are defining iterations to be 10,000. So we are going to run the RANSAC algorithm 10,000 times with some n data points, and we are going to try to fit a line on those n data points. Okay. So now since you are so remember one thing, that here we have, suppose if we have 100 data points, we are out of that, suppose we are choosing some n equal to 2 data points per iteration, right? So since there is a randomness involved here in the selection of the n data points per iteration, so we set something called a seed. Okay. So in your basic coding class also you may have seen this seed. So whenever you are generating something random, if the seed is fixed, then if you run the code multiple times, you will get the same random number. If the seed is not fixed, at every iteration you will see different values, which may result in not so desirable results, or it may result in a bit different result than what you got the last time. Okay. So in order to fix the randomness, in order to make it deterministic, you generally use a seed, you fix the seed. Okay, in this way. Okay. So now there are some more variables. So close points I will come to in a bit. So best error is what? So we are basically trying to see, like given the set of n points, what is my error? Okay, in the first iteration. In the second iteration, I will see whether whether in the second iteration I have been able to reduce my error from the first error. So that is why we need to store a best error variable in order to store what is the best, what are the best n points at a particular iteration, across the iterations basically. And similarly, you have the best coordinates, and all these values are for the best epoch. Yeah, for the best iteration, I mean. Yeah. Okay. So max iteration holds the iterations, which was set to be 10,000 if you remember, and we are also storing a threshold. Okay. So threshold is what? Threshold is basically, like I said, when we draw a curve, when we fit a curve on the n points that we had randomly selected, we are looking at the close neighborhood of it, and how close that neighborhood is given by this threshold and this formula, which you can go back and look at once again. Okay. So you have a coordinate array, and you are initializing it to be you are just initializing it. Okay. So next what do? You you basically you have to, so you have this max iteration which is 10,000, and you remember the self dot iterations which was above, so this was set to be 0, right. So we are basically going to iterate from 0 to the number of max iterations which in our case is 10,000. Okay. Next point, very simple. So I have a set of suppose 100 points, I am going to select 2 points out of them randomly. Okay. So what they are saying is sample random points to be inliners. Okay. So sample without replacement, we are saying out of the 100 points sample some 2 points, okay, n equal to 2 in this particular example. Okay. So this kind of gives you what are the some random 2 points out of all the points that you have. Okay. So now based on the points that you have, you find what is the idea. So you are trying to fit a point, yeah, so based on this particular, based on these particular points. Now yeah, so here you can see that you are trying to predict your based on the beta that you found, you are trying to predict. So that is the predictions are given by, so basically it's if we go back to this function once again, so it's like given an x, it's giving you the corresponding y's based on the betas that you found. Okay. So now you have this error, so error is basically y minus the predicted values. Okay. And now what you need to do next is find coordinates of points having error less than threshold. So the line that I have fitted, which points, I mean what are the points, what are the coordinates of the points that have error to the from the line basically, which is such that the error is less than a threshold. Okay. So that is given by this particular loop. Okay. And now what you find, yeah, next what you find is what are those points in the next part, like which are within that threshold. Okay. So if so that is given by this part actually. So if your if your error for each point is less than the threshold, then you keep it, otherwise you do not keep it. Okay. So these are the inliers that you got based on this. Okay. And then you find like what is the number of inliers. So like I said, at a given iteration, suppose ith iteration, if you see that the number of inliers, which means that the number of lines, the number of points that are lying within the neighborhood of that the line that you fitted, if it is what do I call it, if it's higher than that of the previous iteration, that is I minus 1, you keep this this set of beta, you save this set of beta, otherwise you move on. So now we have an if block which says that number of inlier, which checks if the number of inlier points that you have now is greater than the previous number. So the close points is given by the close points variable that we found is given by this. So if it's greater than 1 in the first iteration, if it's greater than 1 the number of inliers, I save it, otherwise I do not. Okay. So now I will find the mean squared error. Okay. In the inlier between the inlier points, between the y correct true y's of the inlier points and the predicted inlier predicted y's, right. And if the error for the current model is less, okay, and they have more points, so what is it? So the length of the also this particular thing, which basically tells you how many points are there in your in the neighborhood. And so suppose it's greater than the close points. Okay, close points is the initial value that you had, and your current model error, so this is given by this, is even better than your previous model error, right. Then you will update the model parameters. What do I mean by this? This means that first of all, suppose in iteration 1 or suppose in iteration 10 I find that the number of inlier points is 20. In the iteration 50 again I find the number of inlier points to be 20. Now which do I save? The easiest way to see that is that what is my model error at iteration 10 and iteration 50. If the model error is lesser for 50, then we keep that. Otherwise if it was more lesser for 10, then we discard the one for 50. Okay. So, now you can see that we save all these values that are there, okay, and we update all the variables. Okay. So, this is what is happening, and in this way basically we are also saving the all the parameters, all the model errors and so on. And once that is done, so once all of this is done, this entire loop is done, in the next step we increment the number of iterations to +1, so that we tell the model, we tell the code that we have reached one more iteration. And so now based on the best fit x and best fit y that we got, so best fit x and best fit y are what? Basically the number of those points, those inliner points for which we found the fitted curve to be the best. Okay. Best means what? That in the neighborhood we have maximum number of points. So, for them now we have already saved those points in this best fit x and best fit y, and we have the order. So, we will compute the final coefficients using self dot beta once again, and that is what we will return. Okay. That becomes our final point. So, have a look at this code. So, this particular code is just for visualization. Okay. Okay. So, this particular, so this is an example, this block of code that I showed, this shows you the entire nitty-gritty of the ransack algorithm. And now you have again another data set that is already there on our servers, and that basically shows you what happens for 2D data. Okay. And so yeah, so let us see one thing. So, here what you are trying to do is you are already using, so this particular we have this regression class. So, you use this regression class and you solve this problem for as you can see, yeah. So, you solve this problem for the new data set that we have, and they have shown the visualization for it. So, I will just, yeah, okay. So, you can see that there are so many, so in this example, so these blue points are the ones that are the proper points, and the green ones you can see this, so these are very easy to spot. So, these are all like outliers. Okay. So, with these outliers, your curve that you are trying to fit will be always affected. So, if you try to fit a normal polynomial regression, I mean some curve on top of the entire data set, then your curve will not be very good. But in this case, because ransack is able to ignore the outliers, it will be able to fit it around these blue points. So, that is how this algorithm works. So, yeah, in some parts I went a little bit fast, but that is because I want you to look at it and try and understand what is going on, and maybe some like for example sample without replacement. So, what you can do is you can run this code, you can once we upload it, and you can maybe print it and see like what the sample without replacement is actually generating for you, right. So, yeah, so you do basically, yeah, you run all these lines of codes, you print out, you see what is going on with these lines of codes, and then it will become much more clearer for you to understand what is going on internally, right. So, this piece of code is exactly what the ransack algorithm is doing. So, once you get to learn, once you play around with it, you will get a much better idea of what is going on, right. So, yeah, I mean go back after the session and maybe have a good look at what is going on, and also try to maybe in place of this you can generate your own random data, and you can basically run the ransack algorithm on top of that, and you can see like how it's basically taking care of the outliers. So, you can fit maybe a polynomial of, so here it is a second order polynomial, maybe you can go for a 10th order polynomial, and you can try to fit it and see like how it is ignoring the outliers. And mostly like also you can try to fit a line here and see that not for normal linear regression what you have, and for this ransack algorithm, what you are what kind of line you are getting. So all of these playing you should do. So that is why we go through the code a little bit quickly, so that you can go through all of these steps by yourself, because unless you go through them by yourself, you will not learn most of the things. So that is the idea behind running with these codes in such a fast manner. But yeah, I mean, we are kind of giving you some ideas on what these individual functions represent, and the rest is up to you to go back and play around with these individual lines, printing them, seeing the shapes of the vectors that are getting generated, matrices vectors, so that you will get a very clear idea of what is going on. So cool, I have nothing more to share today. And is there programming assignment? Yeah, so how can we solve it? So if I assume it's for your assignments. So assignment part I am not supposed to discuss with you. So if you run into any trouble, if you have any questions, then you can directly ask on the portal in the discussion forum. You can reach to the TAs maybe, but as far as I am concerned, I am not supposed to help you with the assignments. So I can only like share with you some code snippets that is already prepared. So for example, ransack this week, sift we showed last week, and many more things. So it's your job. For the last assignments, okay, I actually do not have access to the assignments. So yeah, maybe whatever questions you have, it's better that you post on the discussion forum, so one of us can get back. So it will be better if you do it that way, and wait to see if the solutions are shared with you. Cool then. So so this is what I had in mind. So next week onwards, so previous week I actually mistakenly said that this week neural networks will start. So that was wrong. So next week onwards we will start with neural networks. So we will have a lot of fun with that. But while neural networks is lot of fun, so all of these algorithms, as I keep saying, these are the classical algorithms of computer vision and image processing. So you should learn all of them, because you'll never know in what situations they will be helpful to you, because they are not data dependent at all. Whereas you'll see machine learning and especially deep learning requires millions of data points, which you may not have all the time. So these algorithms that we have taught you, they are like very important, and you should go through them as much as you can along with the codes. So thank you everyone. We'll meet next week then.